Think back to a moment in the last 8 days where you connected two things that should have worked but they didn't. Geometry showed up in a wrong place, something duplicated strangely, sizes came out wrong for no visible reason. 9 times out of 10, the cause is data trees. Today, I'm going to give you the clearest explanation of data trees you will find anywhere. Once this clicks, and it will click today, you will understand the root cause of most Grasshopper errors and exactly how to fix them. Here's the analogy that makes this permanent. Picture a filing cabinet in an architecture office. The cabinet has drawers, say there are 3 of them. Drawer 1 holds 5 sheets for project A. Drawer 2 holds 5 sheets for project B. Drawer 3 holds 5 sheets for project C. The whole cabinet is the data tree. Each drawer is a branch. Each sheet inside a drawer is an item. The label on each drawer, its address, is the path. In Grasshopper, those drawer labels looks like this: 00, 01, 02 and goes on. Read 01 exactly like a drawer label, it's branch 1 inside a very first grouping level. Don't worry about memorizing every digit today. Just recognize that each set of numbers in curly braces names one specific branch. A plain list. What we covered on day 8 is just a filing cabinet with single drawer. Everything piled up into one place, no separation. So, when does Grasshopper actually build a tree with multiple drawers? The answer is whenever it needs to keep separate groups of data from getting mixed together. Divide 3 different curves into points, and Grasshopper needs a way to remember these 5 points came from curve 1, not curve 2. That's exactly what a tree with 3 branches does. Use the Rhino interpick command 3 times to draw 3 separate differently shaped freeform curves anywhere in the scene. Switch back to Grasshopper. Double-click canvas, type curve, place a curve parameter. Right-click the curve parameter, set multiple curves. In the Rhino viewport, click all 3 curves in sequence, then press enter to confirm. Double-click canvas, type divide curve, place it. Connect the curve parameter to divide curve input C. Set a n input to 5. Add a panel to P output of divide curve, rename it tree output. Look closely at this panel. It's organized into groups and each group has its own header. The first header reads 00, that's branch 0. Underneath it 6 points, indices 0 through 5. Next header 01, branch 1. 6 more points underneath, belonging to the second curve. Then 02, branch 2. 6 more points, belonging to the third curve. 3 curves went in. What came out is a data tree with 3 branches, 6 items in each. Grasshopper used the tree structure specifically to keep the 3 curves point from getting mixed together, which is exactly the job a data tree exists to do. Double-click canvas, type flatten tree, place it. Connect the divide curve points output P to flatten tree input T. Add a panel to the flatten tree output, rename it flattened. Compare the two panels. Before, 3 branches, 6 items each, 18 points total organized by curve. After flattened tree, one single branch 0, holding all the 18 points in one pile. Flattened tree permanently erases the grouping. Grasshopper no longer knows or cares which of those 18 points came from which curve. Use flattened tree when the grouping genuinely doesn't matter anymore. For example, placing a spear at every single division point regardless of which curve it came from. Don't use it when you still need to treat each curve's point differently, because once you flatten, that distinction is gone for good. As an alternative to the standalone component, right-click directly on the panel's input wire and choose Flatten from the context menu. The standalone flatten tree component sitting on the canvas and a small F icon that appears on an input when flatten is applied via right-click. Both do the exact same thing. The standalone flatten tree component is easier to spot when you are reading someone else's file or your own file 6 months from now. The right-click version is faster while you are actively building. Use whichever fits the moment, just know both exist. Double-click canvas, type series, place a fresh series component, start 0, step 1, count 10. Double-click canvas, type craft tree, place it. Connect series output yes to craft tree input T. Add a panel to the craft tree output, rename it crafted. Before crafting, one branch, 0, holding all 10 numbers together. After craft tree, 10 separate branches, 00, 11, all the way to 99. Every item now has its own private branches all by itself. Craft is the opposite move from flatten. It takes a pile and gives every single item its own drawer. It looks like it makes things more complicated for no reason right now. In next section, I'll show you exactly why this is one of the most useful moves in all of Grasshopper. Here's where data trees stop being an abstract idea and start being genuinely powerful. When you connect two different lists or trees into the same component, say points into a circle component and radii into the same circle component, Grasshopper has to decide how to pair them up. It does this branch by branch. Branch 0 of one input is matched with branch 0 of the other, branch 1 with branch 1, and so on. If both inputs are flat, single branch list, everything gets matched item by item, position for position, which is exactly the diagonal problem behavior you will see on tomorrow's lesson. But if one input has been crafted into multiple branches, each of those branches gets matched against the other's input's entire branch. That's how one crafted branch can apply a single value to the entire group. Double-click canvas, type circle, place a circle component. Connect the divide curve points output P to curve input. Add a single number slider radius value 5 connected to the circle's R input. Now add 3 separate number sliders 5, 7 and 9. Double-click canvas, type merge, place a merge component. Connect all 3 sliders into merge 3D inputs. Now add a graph tree component. Connect the merge output to graph tree input. Connect circles R input to come from this graph tree output instead of a single slider. The merged list 1, 2, 3 just got crafted into 3 separate branches, branch 0, 1, 2. That's 3 branches of radii matched against our 3 branches of points, 1 branch per curve. Confirm in Rhino. The first curve circles are now radius 5. The second curve circles are radius 7. The third curve circles are radius 9. The tree matched. 3 branches of radii lined up with 3 branches of points branch for branch. Each curve's entire group of circles picked up that branch single radius value. That's tree matching, works exactly as intended. Double-click canvas, type tree statistics, place it. Connect the divide curve points output P to tree statistics input D. Add 3 panels to its 3 outputs. Rename the panels branch paths, path count and total item count. Tree statistics is your diagnostic tool. It doesn't change the tree at all, it just reports on it. Paths. List every branch's addresses currently in the tree. Path count tells you how many branches exist. Data count tells you the total number of items across every branch combined. Double-click canvas, type path mapper, place it. Connect the divide curve points output P to path mapper input D. Double-click the path mapper component to open its editor. In the source field, type bracket A semicolon B bracket. In the target field, type bracket A bracket. Click OK. Add a panel to the path mapper output, rename it remapped paths. Path mapper lets you rewrite branch addresses directly. The source field describes the pattern of paths coming in. Here, A and B are just placeholder letters standing in for whatever numbers actually appear in each path. The target field describes what you want those paths turned into. Our original tree's path looks like 0, 0, 0, 1, 0, 2. 2 numbers per path matching the source pattern A and B. The target pattern A tells path mapper keep only the first number, drop the second. So 0, 0 becomes 0. Path mapper's real value shows up on deeply nested trees several levels deep where you need to stripe out or reorganize specific levels of the address without touching the items themselves. It's an advanced tool, you won't need it constantly. But when a tree structure is technically correct yet organized the wrong way for what you're building, Paths Mapper is how you fixed it without rebuilding the whole tree from scratch. You may need to watch this video twice. That's completely normal. Data trees are the hardest concept in Grasshopper, and you just got a clearest version of it that exists. Tomorrow, we put this straight to work, building a fully parametric point grid using a graph cross-reference technique. It's all where all today's theory turns into something visually satisfying. Subscribe and I'll see you at day 10.